Okay, good morning. What we're going to do today is take the idea of integrals just a tiny step further. And before we do that, and before I even write the title, I want to start with an example, which is not an example about integrals at all. So here's a square. And suppose this square is of area 1. It's a 1 by 1 squares. 1 by 1 square. Let's say this looks more like a foot than a meter, so let's say this is a foot by foot square. And I'm going to add areas in the following way. I'm first going to add 1/2 of the square. So this is 1/2. Plus, now I'm going to add 1/4 of the square, which is 1/2 squared. Now I'm going to add 1/8 of the square, which is 1/2 to the power 3, and so on. Dot, dot, dot. I hope you can see the dots. So 1/8, and then 1/16, and then 1/32, plus 1/64, plus 1/128, plus 1/256, plus 1/512, plus 1/1024, plus 1/2048, plus 4,096. That's it. Okay? So there's a dot, dot, dot here. I'm going to add on areas forever. And although I keep on adding area, the total area is bounded. It will never exceed, it will never even reach the area of 1. Do you agree? So the concept of infinity, which I hope you kind of got used to by now, is a tricky concept. You approach it, but you never reach it, and all kinds of maybe intuitive ways of getting used to this term. But here's another way. We can add up area more and more and more, and yet have a total bounded area, not have an infinite area, although we keep on adding. This phenomenon is more related to our next topic, which is series, and I want you to remember this example. Today we want to do this in a similar context, in the context of areas under graphs. What we want to do is say, now let's say we're looking at a function over an interval that's not necessarily a bounded interval, not an interval of the form AB, but maybe an interval of the form A infinity. So for example, if we look at this function, this is the function e to the minus x, that's its graph. It gets closer and closer and closer to the x-axis here. I don't know if you can see it. It never really touches it, right? No matter how big x is, e to the minus x is never going to be 0, okay? And what we want to do is calculate the area under the graph, intuitively speaking, between, let's say, 0 and infinity, all the way to infinity. And the area, well, you can kind of draw it, but you can only draw it as far as a finite place, because we can't draw all the way to infinity. But if we go further and further, we will still be adding area. Do you agree? Nevertheless, the total area is going to be finite, just like here. Although this x-axis goes on far, far away to infinity and beyond. Okay? So how are we going to formalize this statement? How are we going to give a meaning to something of the form a to infinity? That's what we have to define. Okay? And the way we're going to do it, is basically, we're going to say, let's take the area up to a finite point, call it m, And let's take m to infinity. That's going to be the definition that I'm going to write now. Okay? So this is the idea that we want to discuss today, removing the assumption that we're only integrating on finite intervals. And a bit later, what we're going to remove is the assumption that we're only integrating bounded functions. We're going to allow functions to go to infinity, so kind of mimic this idea on the y-axis. So let's start making things formal. So our title is improper integrals. That's what they're called. And here's our first definition. So let f be a function defined on this infinite interval, f from a infinity to r, be a function which is integrable in the usual sense on am, on a finite interval. This is the only intervals for which the term integrable makes sense, for every m. So if you go up to m, it's integrable. In the usual sense, Riemann sums, converge, blah, blah, blah. We define the integral from a to infinity of f to be the limit as m goes to infinity of the integrals from a to m of f. That's the definition. Providing, of course, that the limit exists. And we'll see that in some cases it doesn't. And if it doesn't, if not, we can always write this, we can always put f in a snake, but it just won't make sense. So if the limit does not exist, we say that the integral diverges, or just doesn't exist. Okay? So let's do an example, and maybe let's start as a first example. Let's do this e to the minus x, which we already drew. So example 1, suppose we want to calculate the integral from 0 to infinity of e to the minus x. We want to calculate this area. And I hope you're convinced that there is a chance that it actually makes sense. So by definition, it's the limit as m goes to infinity of the integral from 0 to m of e to the minus x dx. Now this thing is already a regular, good old, finite, definite integral, right? Integral on a bounded interval of a bounded function. How do we solve this? Right, Newton-Leibniz. We find the antiderivative calculated at m minus calculated at 0. So this is the limit. M goes to infinity. The antiderivative of e to the minus x is e to the minus x, but when you take the derivative of this, there's a minus which you don't want, so you have to add this minus here to cancel it out. Evaluated between 0 and m. So here we use Newton-Leibniz, not on this thing, on the regular definite integral. This equals the limit as m goes to infinity. And now I'm plugging in the values. Minus e to the minus m minus the lower bound, minus makes it a plus, e to the minus 0, which is e to the 0, which is 1. Good? As m goes to infinity, e to the minus m goes to 0, so this limit is just 1. So intuitively, the area under the graph of e to the minus x from 0 to infinity is 1. In the sense that if you stop at further and further and further points, you're going to get closer and closer to 1, never to exceed it, just getting closer to it. Clear? So that's example number 1. Let's do another example. Suppose we want to calculate so this is example 2, the integral from 0 to infinity of cosine x dx. So the picture here is, well, we all know how cosine looks, right? Something like this. This is cosine. A naive guess might say that, well, we have this positive and negative areas, maybe they cancel out, right? But that's not gonna fit in with the definition we just defined. If you think about it, these positive and negative areas cancel out only if you stop at very specific points. But as you go further and further out towards infinity, you add, then you subtract, then you add, then you subtract, and it's not approaching. The total area doesn't approach a fixed value. Do you see that? Is that convincing? Okay? And by definition, we're going to see as well that this thing is not defined, or is diverges. So this is the limit, as m goes to infinity, of the integral from 0 to m of cosine x. By Newton-Leibniz, this equals the antiderivative, which is sine x, evaluated between 0 and m. So it's the limit, as m goes to infinity, of sine m minus sine of 0, which is 0. And as m goes to infinity, sine doesn't have a limit. So this thing, sometimes people write DNE for does not exist, or you can write diverges, or whatever. Okay? So the limit doesn't exist, therefore the integral does not exist or diverges. That was the definition. Okay? Okay. So those are two examples. Some remarks. So remark number 1, we similarly define, I'm not going to write the full definition, just the crucial part of it, the integral from minus infinity to some a of f to be the limit, as m goes to infinity, of the integral from, or well, we can do, yeah, from minus m to a of f. Or you can write m goes to minus infinity and just write m here. It doesn't matter. Okay? So that's for an interval which is unbounded on the negative x-axis side. And of course, the full definition is the way we wrote it there. We define this, providing the limit exists. If the limit does not exist, blah, blah, blah. We can also define such a notion for a function which is defined on all of R. So if f is defined on all of R, we define the integral from minus infinity to infinity of f. And this, there are two conceivable ways to define it. And one is the way it is actually defined, and the other is not. And they're not equivalent. So the way we defined it we define it is as the sum of the integrals from minus infinity to a of f plus the integral from a to infinity of f. And one can prove that it doesn't depend on a. You can choose whatever a you want, and usually people just choose 0 because that's kind of the easiest. Okay? And providing both integrals on the right-hand side, RHS stands for right-hand side, converge. That's the way we define it. You may think that a reasonable way to define it could also be to say that the integral from minus infinity to infinity is the limit as m goes to infinity of the integral from minus m to m. Right? That would also make sense. It turns out not to give the same thing. Okay? One can show by examples. Maybe we'll see some later. And that's not how we define it. There is such a notion, but we're not going to discuss it here. That's the way we define an improper integral on the entire real line. Okay? Clear? Okay. It's very important to notice that it's defined via a limit. Okay? As is almost everything in this course. I think by now you've realized that. Okay? So everything you want to do, every step you want to make in calculating always comes before you calculate the limit. You write it as the limit of these things on these things. These are regular definite integrals. You can use the entire theory of definite integrals in order to calculate them. Then you need to take the limit. Okay, just like we did in the examples, and we'll do more. Yes?
Why can't we just use the limit as n goes to infinity of the integral from minus m to m of f of x?
It's not that you can't use it. What I'm saying, the question was, why can't we define it to be as the integral from minus m to m? It's not that you can't. You can, but it turns out not to be the same thing as this.
Why not?
Well, one has to show examples where this gives something and a different thing gives something else. Okay? A typical example would be, we'll get to it. If you remember to ask me this in 20 minutes, then I'll be able to answer it with an example you can easily relate to, because I need to do some more examples. Okay? But I can show you easily an example where this, for example, does not exist, whereas the other limit would exist. Okay? So we need to choose one, and this is the one we choose, not we. This is the one typically chosen for this definition for various reasons. And I'm just emphasizing this so you don't try on your own to say, okay, I'm going to calculate it differently by minus m to m, because you're going to get not necessarily the same thing. Okay, so let's do some more examples. That's the right thing to do now. So here's example number 3. Example number 3. Suppose we want to calculate the integral from 1 to infinity of dx over x, of 1 over x dx. So this equals, by definition, the limit as m goes to infinity of the integral from 1 to m of 1 over x dx. Right? Now we can use Newton-Leibniz. What's the antiderivative of 1 over x? Right, it's ln of absolute value of x, but since on the interval we're working x is always positive, we don't need the absolute value. So it's just the limit as m goes to infinity of ln of x evaluated between 1 and m. So here I just used the Newton-Leibniz formula. This equals the limit as m goes to infinity of ln of m minus ln of 1. What's ln of 1? 0. So it's just this. And what's this limit? Right, the limit is infinity, which means the limit doesn't exist in the finite sense, and therefore we say that this thing, the integral from 1 to infinity of dx over x diverges. Do you agree? Okay. So note that if we just try to draw this, what is the picture that corresponds to this? Well, 1 over x looks something like this, right? We're only interested in the interval from 1 to infinity, so we're kind of trying to say, what's this area? From a naive perspective, this looks exactly like the drawing of e to the minus x, right? It's a function that goes to 0, and we're trying to calculate the area. But it's very different. The area here is not bounded. If you go far enough, you can accumulate area as much as you want. How much area? Well, I can tell you exactly. If you go up to m, the area you're going to accumulate is ln of m, right? Do you see that? So if you want to accumulate an area of 1 million, well, take ln of 1,000,000. That's how far you have to go in order to accumulate that area. Okay? So it's not bounded. And therefore, this area, although looking at it, it looks very similar to the e to the minus x graph, here the area is not bounded. So it's delicate. It's not that every time a function goes to 0, the area is going to be finite. Clear? Okay, so this is 1 over x. Example number 4. Yes, in the definition, okay, so let's emphasize here. We say that the integral diverges or does not exist. Both are legitimate terms. And when we say that the limit exists here, I mentioned this throughout the course several times. When we say that a limit exists, we always mean in the finite sense. Okay, we emphasize it separately when we allow it to be finite or infinite. But here, we mean finite. Clear, everybody? Okay. So back here, let's do one more example. So now let's calculate the integral from 1 to infinity of dx over x to the power alpha, where alpha is some any real number, okay? But not 1. So let's write it. Alpha not equal to 1. When alpha equals to 1, we already did it. That was example 3. When alpha is not 1, they're all going to follow the same pattern, so we can calculate all of them at once. Okay? So whenever alpha is not 1, we're going to get the following. The limit, as m goes to infinity, integral from 1 to m dx over x to the power alpha. That's the definition, right? Equals limit, m goes to infinity, and now I need the antiderivative. So x to the alpha in the denominator is like x to the minus alpha, right? It's the derivative of x to the minus alpha plus 1, right? So it's x to the minus alpha plus 1. But the derivative of this is x to the minus alpha times this thing, right? And we don't want it, so we have to divide by it, minus alpha plus 1. Do you agree? And evaluate all of this between 1 and m. Look at it a second and tell me if you agree with what I just wrote. Yep? Everybody? Okay. So now the snake is gone. We just solved it using Newton-Leibniz, finding the antiderivative and looking at the value of the antiderivative between the bounds. So what do we get? There's still that limit. We still have to plug in m and calculate the limit. So it's the limit as m goes to infinity of what? So let's pull this 1 over minus alpha plus 1. We can write it 1 over 1 minus alpha. That's the same thing. Let's take it out of that expression. When I plug in m, I have m to the power minus alpha plus 1. So, or I can write m to the power 1 minus alpha. Minus, when I plug in 1, I have 1 to any power, which is just 1. So this is what I get. Remember, alpha is not equal to 1. That's why this is legitimate, all of this. If alpha is 1, this does not work, but we already did that separately. So what do we get as m goes to infinity? So equals, I'm going to write this in a slightly non-standard way, just to make it compact. So as m goes to infinity, now it depends on what alpha is. If alpha is greater than 1, then 1 minus alpha is less than 0, right? If alpha is greater than 1, 1 minus alpha is negative. So this is like m to a negative power, or 1 over m to a positive power, where m goes to infinity. So the limit of this is 0. Do you agree? So the total limit is negative 1 over 1 minus alpha, or 1 over alpha minus 1. That's if alpha was positive. Sorry, alpha was greater than 1. If alpha is less than 1, then 1 minus alpha is positive, and m to the positive power, where m goes to infinity, goes to what? Infinity. Good? Questions? Okay. So the conclusion is, if alpha is less than 1, this thing diverges. The area is infinite. It would be like in this picture. If alpha is greater than 1, this thing converges, and we even calculated it. And the area, well, we know what it is. It's 1 over alpha minus 1. So if I drew this exact same picture, but told you, hey, this is not 1 over x, this is 1 over x squared, it would look very similar to this. Only if you draw them on the same graph do you notice the actual difference, right? But if this is 1 over x squared, that means alpha equals 2, then this area does exist. And we can even say what it is. It's 1 again. Clear? Very tricky business. Very delicate business. 1 over x squared, the area from 1 to infinity converges, and it's 1. 1 over x, the area diverges. 1 over x doesn't approach the axis fast enough. Okay? Intuitively speaking. Good? This is stuff that it really challenges the intuition. It really challenges the intuition. Okay? So altogether, we can deduce a result here that this integral converges if and only if alpha is greater than 1. Let's write that. Because if it's less than 1, it diverges, and if it equals 1, it diverges as well. Okay? So the conclusion here, let's write it on a separate board because we're going to use it. So the conclusion is so we can actually call this a theorem, and we're going to use it often. The integral from 1 to infinity of dx over x to the power alpha converges if and only if alpha is greater than 1. And we just proved this theorem by actually calculating it by definition. Okay, so it really is, in a sense, counterintuitive or challenging the intuition that when you look at 1 over x, the area is not bounded under the graph. And when you look at 1 over x squared, and I'm doing the same thing with my hand, the area is bounded. The area is finite. Okay? Okay. Moving on. So remember when we defined definite integrals, we had 2 restrictions. 1, bounded functions. 2, bounded intervals. We now extended the theory to unbounded intervals. Can we handle unbounded functions? So again, let's start with an example. So this would be example what? Example 5 for today. Let's calculate the integral from -1 to 1, finite interval, of dx over x squared. So what does this equal? It's the antiderivative, so it's -1 over x, right? This is x to the -2, this is x to the -1, and the minus cancels it. Do you agree that this is the antiderivative? Everybody? Evaluated between -1 and 1. This is Newton-Leibniz. Good old Newton-Leibniz, right? It's a finite interval, right? What do we get? We have to plug in 1 minus plug in -1. Let's do it carefully because there are a lot of minuses running around here. When we plug in 1, we get -1 because of this minus. Do you agree? Minus, and then this minus makes it a plus, but we plug in -1, so we get -1 again. Did everybody follow that step? Okay? A lot of confusing minuses. So -1 minus 1 is -2. Good? Now let me show you what we just got. The function 1 over x squared, which I hope you know well, it's on your list of functions and graphs, which is on your fridge and above your bed and everywhere. Looks like this. Right? And we calculated the area under the graph, the definite integral, from -1 to 1. And we got that the area under the graph of this function is -2. Do you agree that something went very wrong here? This is nonsense. Do you agree? Okay. What went wrong? Right. The function is not bounded. It's not bounded near 0. When x approaches 0, from both sides, it goes to infinity. This is not a bounded function. The entire theory collapses. The standing assumption throughout all our discussion last time and every time we mentioned definite integrals was bounded function. So I'm going to put a big orange, maybe we have some red here. No red. Red. There we go. I'm going to put a big red X here. This is wrong. Nonsense. And the reason that it's wrong is that we just used tools, theorems, that we derived and proved and everything for definite integrals on something that's not a definite integral, because definite integrals were for bounded functions. And we just so happen to also get a silly answer, so we can believe that this is nonsense. So what can we do? Okay? Just like before, for an unbounded interval, we have to extend the definition of the integral for an unbounded function. And let's do that. Let's write the definition. So, maybe let's write it here. under this. So definition. Suppose f is a function from an interval of the form ab to r, where it's closed at a and open at b, and this is important, which is integrable on a b minus epsilon for any epsilon. Well, as long as b minus epsilon doesn't pass a to the left. Okay. So what I'm looking at, the picture to go along with this, is something like this. So I have a, I have b, and the function, the idea I want to capture is an asymptote at b. I want the function to explode at b, to be unbounded at b. Something like this. This is the picture I have in mind right now. And I'm saying, okay, if you take b minus epsilon, so b minus epsilon would be somewhere here, b minus epsilon, from a to b minus epsilon, it's a good old regular bounded function on a bounded interval, and it's integrable. Okay? So suppose f is like this. We define... Can you help me here? How would I define this? I want to define the integral from a to b of f. How do you suggest I define it?
As epsilon approaches infinity, limit as epsilon approaches.
Limit, wait, I have to write this. As epsilon approaches what?
0.
0, good. And let's even be more precise, 0 plus, because epsilon is positive, right? Of what?
The integral a to b minus.
Right, the integral from a to b minus epsilon of f of x dx. And of course, providing the limit exists. So it's the same idea. We say, okay, let's look at the integral from a to b minus epsilon. This is a good old regular definite integral. And now let's make epsilon smaller and smaller and smaller and smaller. If at the limit the area is still bounded, intuitively speaking, if there's a limit to these ever-growing areas, then we call that the area from a to b, although the function is not bounded at b. Do you see that this is precisely the same idea we did on the x-axis for infinite intervals, but kind of doing it on the y? If you look at this drawing like this, you should see that this is precisely the same idea. Do you see that, everybody? Okay. These are trickier than the a infinity integrals for the following reason. They come in disguise. The a infinity ones, you can't mistake them. There's an infinity sitting up there, or a minus infinity sitting down there, and they can't hide. You right away know they're improper, right? When I have the integral from a to b of f, it doesn't shout out and say, hey, I'm improper. It can hide. It can deceive you, just like this example here, right? When you look at it, it doesn't look right away as improper. You have to think about it for a moment and say, wait. 1 over x squared is not a bounded function. This is an improper integral. I have to handle it using that definition and so on. Okay? Do you agree? So from now on, from now on, whenever I give you an integral, even if it looks good old proper integral, you have to pause a second, think, wait. Is this improper? Is it a bounded function or not? If it's bounded, you're good to go with everything we discussed so far. If it's not a bounded function, you have to resort to the stuff we're talking about today. Okay? So let me write a few remarks, and then we'll actually calculate this one using that definition. So remarks. Remarks. So remark number one, we similarly define the integral from a to b of f to be the limit as epsilon goes to 0 plus of the integrals from a plus epsilon to b of f in the event that the function is not bounded near a. So I'm not going to write the full definition, I'll just draw the drawing for this situation where you have a and b and the unboundedness is not at b but rather at a. So for a picture like this. So you would define it like this. Clear? And the second remark, if the situation is like in the 1 over x squared example, if the situation is that there is a c somewhere inside the interval, not necessarily in the middle, somewhere inside the interval, and the function is not bounded at c, at a point inside the interval, so a situation like this, then we define the integral from a to b of f to be, what would your guess be? Exactly. Very good. The integral from a to c of f. And this is already an improper integral, which has been defined in the original definition. It's this thing, this chunk, plus the integral from c to b of f, which is again improper. It's this one, the right part of it, which has already been defined up here. And this thing is defined providing both of these, providing both right-hand side integrals, improper integrals, converge. Okay, do you see the analogy to the remarks and to the statements concerning the unbounded intervals that we had previously? Okay? And yeah, so having these, let's try to calculate now the example which we wrote nonsense for before, namely 1 over x squared between -1 and 1. Do you agree that it falls under remark 2? Yep. Okay, so let's go back to here. So we said this was nonsense. Let's try to calculate this. In order to calculate it, we have to break it into two improper integrals, from -1 to 0, plus from 0 to 1, to calculate each of them separately. And if both converge, we add them, and that's this thing. Do you agree? Okay, so the integral from -1 to 1 of dx over x squared, this is improper, We break it into the integral from -1 to 0. And here we don't have a choice where to break it. We have to break it at the point C where it's not bounded. In this case, 0. Plus the integral from 0 to 1 of dx over x squared. And we need to calculate each one of these improper integrals separately. Okay? So let's do this one first. So the integral from 0 to 1 of dx over x squared equals, what should I write now? Limit, good, of what? Epsilon goes to 0 plus, of the integral from what to what? 0 plus epsilon, so let me just write epsilon, to 1. Do you agree? Of 1 over x squared. Do you agree that this is what I need to write by the definition? Yep? Okay, what does this equal? Well, it's x to the -2, wait, limit, I have to carry that limit along. It's x to the -2, that's the derivative of what? Right, -1, well, the Newton-Leibniz step is going to be the same thing, right? It's still the antiderivative of this function. Evaluated between what?
0, 1.
Not 0, 1. Epsilon and 1. And then take epsilon to 0. Right? So what do I get? I get the limit, as epsilon goes to 0, of -1 minus plus 1 over epsilon. Do you agree? What happens as epsilon goes to 0? It's infinity. So this area here, what we just showed, is that intuitively speaking, this area here does not converge. It's infinite area. It's not a bounded area. Therefore, this thing does not exist. So this thing does not exist. That's what we just showed here. And we don't even have to do the other one, right? Because only if both exist, then we can say that the sum is their sum, that this is their sum. And therefore, so the conclusion is that this integral from -1 to 1 of dx over x squared diverges by definition. Good? Clear? It's infinite area. It's not bounded area under that graph. So what I want to do is give you to try one on your own. So let me erase this definition. And I'm purposely erasing it because I want this specific board right now. So example 6, which I want you to try on your own. Example 6, wait, I want to leave some space here. So example 6, show that the integral from -1 to 1 of 1 over x diverges. And when I say show, I mean calculate it using the definition. What does this function look like? Hopefully you all know. So if this is 1 and this is -1, the function 1 over x is this hyperbola, right? It looks like this. And we're only looking at this part of it. Right? This is what the function looks like. Do you agree? And this is what the function looks like. And what you need to do is the same as before. It's unbounded at 0. You have to break it from -1 to 0 and from 0 to 1 and calculate each one separately by definition. And at least one of them is not going to exist, and therefore it diverges. In fact, both are not going to exist. Both are going to be infinity, and therefore it diverges. Although it's very tempting to say that, wait, this is symmetric. Isn't it tempting to say whatever the answer is here, whatever this area is, it's precisely the minus of this area, right? It's really tempting to say, hey, that integral has to be 0, but it's not, because that's not the definition that we gave. Okay, so it turns out that this is infinity, and if you want to think of it that way, this is infinity minus infinity, and infinity minus infinity is not 0. And even if you press further and say, wait, but this is not just infinity minus infinity, this is precisely the same infinity minus infinity, it has to be 0. Well, it could be, but not by the definition we gave. The definition we gave strictly required that both of these have to be finite. Okay? Good? And what I want to add here now to this theorem is, and it's a dual to this one, but I'm not going to prove this one. You can try it on your own. The integral from 0 to 1 of the x over x to the alpha converges. So this is these family of integrals where we allow alpha to be whatever, if and only if alpha is less than 1. So both the examples we had, alpha was greater than or equal to 1. Here alpha is 1, and in the previous example alpha was 2, and they both diverge. If you take alpha to be 1/2, for example, it's going to converge. So 1 over root x converges on 0, 1. On 1 infinity, it's the opposite. Okay? And you have to remember these two facts. They're extremely useful. We're going to use them a lot. Okay? Maybe let's let's do one more example just so you actually see it. Let's do the 1 over root x, for example. So, example, what? 7. If we take the integral from 0 to 1 of dx over root x, so this is x to the power 1/2. This is alpha equals 1/2 in that theorem. What do we get? We get the limit as epsilon goes to 0 plus of the integral from epsilon to 1 of dx over root x. You have to identify that this is not bounded near 0. As x approaches 0, 1 over root x goes to infinity. Do you all see that? Yep. Okay. What's this thing? Newton-Leibniz. I have to calculate the antiderivative. So this is x to the power minus 1/2. It's the derivative of x to the power minus 1/2 is the derivative of x to the 1/2, or root x. Right, so we have to fix it a bit. So the derivative of x to the 1/2 is 1/2 x to the minus 1/2. We don't want that 1/2, so we have to plug in a 2 here. And then evaluate this between epsilon and 1. This is our Newton-Leibniz step performed on what's sitting inside here, on the definite integral, for which it's legitimate. This equals limit epsilon goes to 0 plus of 2 times root 1, which is 2, minus 2 root epsilon. As epsilon goes to 0, this goes to 0, and the limit is just 2. So the area under 1 over root x between 0 and 1 is finite. The integral converges, and note again, its improperness is hidden. Only after you recognize that the function is not bounded, do you realize that it's improper and you have to do this rather than just solve it using Newton-Leibniz? Clear? Questions? Yes?
Is the second theorem for any, if it goes from 0 to any finite number, or does it have to be 0?
This theorem?
Can it go to 2?
Okay, good question. So the way I wrote it, it's between 0 and 1. If you want to take it between 0 and 5, for example, the value of the integral would be different. But whether it converges or not would not. Why? Because what's the integral from 0 to 5? It's the integral from 0 to 1 plus the integral from 1 to 5. And the integral of this function from 1 to 5 is not improper. It's a regular, definite integral. Okay? Likewise here, by the way. The fact that I wrote 1 here is, well, that's the standard way of presenting this theorem. But you can write any a greater than 1, or any a greater than 0, in fact. The integral from 5 to infinity converges if and only if alpha is greater than 1. Okay? The remaining chunk between 1 and 5 is proper, is a regular definite integral, and does not affect the convergence of the improperness of this thing. Clear? Good question. More questions? Okay, so let me see if I have anything I want to remark further, or is this a good time to take our break? Yeah, let's take our break now. 10 minutes.